All right, in this video, we are going to look at the counting techniques we did in the last section and apply them to probability problems. Some of the problems we'll be able to do this way are much more advanced than we were able to do even before we talked about the counting methods. So let's take a look and see what this first problem is. I want to use this as a way of motivating the way we think. All right, first, when you see any of these problems about marbles, do this. Make yourself a note that the total number of marbles is 15. 10 blue, 5 red. Now, we're pulling out 2 marbles. And in fact, it looks to me like you're pulling them out one at a time because it says, assume the first marble is not replaced. So anyways, the question is this. What is the probability that they are both red? Well, first, what we need to get is the size of the sample space. Now, the sample space in this problem will be all 2 marble combinations that you can possibly pull out of the bag. And we know how many that is. Since you pull out 2, whether you pull them out one at a time is not the thing. Nowhere in this problem did it say there was an ordering. So we're just pulling out 2 of them, regardless of order, out of a total of 15. So this thing here is the size of our sample space. So let me put this prominently here. And to remind you how to get to that thing, go and start your calculator. Now remember, the way to do this is you type in the 15 first, then you go over to Math, PRB, and since we want combinations, order does not matter, we choose number 3, and then we put the 2, enter, and we get 105. Now I need the size of the event. So the event will be 2 red marbles is what we want. What's the probability of 2 red marbles? So what you're going to have is you're going to divide by 105. And now we need the size. I need to know the size of 2 red marbles. So how do we get that? Well, since we want to have 2 red marbles, and there's a total of 5 red marbles, we can select 2 red from any of the 5 red marbles. So what we have up there is going to be 5 red marbles, and we are choosing 2 of them. And I think you'll find the 5C2 is equal to 10. A bag of marbles contains 15 blue marbles, 8 red marbles, 12 green marbles. Suppose you reach in and select 2 marbles, one at a time without replacement. What is the probability of 2 green marbles? So in this case, n equals 35. We're choosing 2 marbles, so the size of our sample space is going to be all possible 2 marble combinations from 35. Let me go ahead and get that number down. So remember, one way to save yourself some trouble is to arrow back up here and enter, and then it will allow you to go back and edit what you had there before. So really all I need to do is change that 1 to a 3 and hit enter, and I get 595. Now, I want to be really specific on this. You want 2 green marbles. The fact that you're choosing them one at a time without replacement is not important because we didn't mention order. I did not say one of the marbles is first and one of the marbles is second. Although when I do pull out 1 marble, there's only 14 left. So there's more than one way to do these problems, and I like this way the best. Look what we want. We want 2 green marbles, and we have 15 blue marbles, but we don't want any of them. Then we have 8 red marbles, but we want 0 of them. And then we want 12 green marbles, but we only want 2 of them. So if you look, let me make this specific here. There's the blue marbles, there's the red marbles, and there's the green marbles. That is the size of the 2 green event. So I like this method because you can keep track of all the other ones. If you look at these numbers, 0 blue plus 0 red plus 2 green, well, we're only selecting 2 marbles, so that matches up. Now, if I want the probability of 2 green marbles, I will take this quantity up here and divide it by n of s. Let me finish this quantity, by the way. Anytime you see a 0 here like that, that number is equal to 1. 8C0, that's equal to 1. And then 12C2, well, I'm going to have to use the calculator for that. $66. In the previous problem, suppose we pull out 2 marbles, one at a time, without replacement. What is the probability of getting a blue first and then a green second? So now, since we are doing first and second, we need our sample space is a little bit different, because our first pull, we can pull from any of the 35 marbles, and then the second pull, there's 34 marbles. Together, between the two of these, what do we have? We have 35 times 34. That's 1190. And now, when we look at the event, we need to have, what is what we want? We want the first one to be blue. So if the first one is blue, we had a total of 15 blue marbles. 15 blue marbles out of 35 marbles. Then that one's gone. Now the second marble, we pull out a 14, or I'm sorry, the green marbles, we only had 2 of them. All right, then we have 34 marbles left over. There's still 2 green ones to choose from on the second choice. So this time we have 30 over 1190. So it's slightly different than the last one. Note the similarities between the two of these problems. And let me do this. Furthermore, what is the probability of a green first and then a green second? So it's the same situation. If we want a green on the first marble, we have 2 greens to choose from out of a total of 35 marbles. Then that green, put it away. The second marble that we choose, there's only 1 green left out of 34 marbles. So in this case, we're only 2 out of 1190. So notice the probability is significantly less in this situation than it was before. What is the probability that your 5-card poker hand is all black? Well, as I've mentioned before, when they hand out poker cards, while they count them out to you one at a time, the fact is the order of them does not matter. So we have to keep that in mind. The order is not going to matter. We need to know how many poker hands there are, 5-card poker hands there are. And we get that by doing 52 cards to choose from, and we pick 5 of them without order. Change that to a 52, and then we want a 5 there. Enter. So we got 2598960. So those are the total number of 5-card poker hands that are possible. Now we want only black ones, and we want 5 cards to be black ones. So the way you can set up your event, if you will, I don't know how to write it. Let me just call it all black. How can we have that in our 5 cards? Well, in order for that to happen, we have 26 red cards. We want to make sure that we choose 0 of those. Next, we have, and I should probably put this, let me put an N around it. Yeah, I think in this notation, you can make up whatever notation you want. So I'm going to now, I think I have it. I'm going to say all black. Okay, so we want 26 or 0 reds, and then out of the 26 black ones, we want all 5 of them to be that. And in the denominator, we of course have 52C5. So 598960. Let me, before I actually evaluate it, let me keep this for a moment to show you the power that you have at your fingertips. Now on the top, we already talked about the cards that we have. And notice here, 26 plus 26, that equals the 52 cards. 0 plus 5 equals the 5 dealt cards. And now in the denominator, we have 52C5. Well, let me go. I've already got that number, but I just wanted you to see the structure here. 2598960. Now, as I said before, this 26C0 is equal to 1. And now the 26C5, let's see what that is. 65780. So there you have it, 65,780 divided by 2,598,960. And if you were looking for an approximate answer to this, let me move it out of my way. Roughly 0.0253. Now let me show you the power. So I'm going to give you another question. Let me leave that up for a minute. What is the probability of 3 red and 2 black cards? So last time I was keeping track of these things. That was the black ones there. Red, black. I'm going to do the same thing here. So my probability in this case, let's call it 3R, 2B. So I've got 26 red cards and I want 3 of them. Then I've got 26 black cards, but I only want 2 of them. And once again, I'm choosing 5 cards from a deck of 52. So you can see how the subscripts are very powerful. Now let's go ahead and get all these numbers. $2,600. And then the 26C2. $325. And we've already done this number a few times now. And let me go ahead and get these. Now here's something that you can do too. Let me go up here and grab this guy and I can hit enter. And then if you want, you really don't have to type any new things. You can just kind of click here and grab that guy now. Enter, and then just enter. So I got 845,000 for the numerator. Over 2598960. And the homework is going to be asking you for 4 decimal places of accuracy. So I figured I would throw that in here. Now, when that 845,000 there, all I have to do is click the division button, and it will already put it there for me. And enter, and let's see what we have. Now, I know where the mistake is that I've made, but look right here. This answer, this is a probability that I'm trying to get. I know for a fact that no probability is ever going to be bigger than 1. So you know that this is wrong. I must have made a mistake, and I know where I made the mistake. This happens all the time with me because the keyboard that I use and this calculator do not always agree. I needed a 6 0 instead of a 0. And now, let's see what we have. Ooh, crushing. I took the answer again, so let's do this. Divided by 2,598,960. Finally, what are we going to get? 0.3251. And if you want, somewhere in the homework, they ask for a percentage even, I think. So you can use, instead of that, you can use 32.51%. So a percentage to 2 decimal places is the same as a decimal to 4 decimal places. What is the probability of a royal flush. And I realize I may have to explain that to you. It's still a 5-card poker hand. So the size of our sample space is still going to be 52C5, which is the 2598960. Now, what is a royal flush? A royal flush looks like this. 10, you'll get a 10, and then a jack, and then a queen, and then a king, and then an ace. And they all have to be of the same suit. So we have 4 different suits. We can have all diamonds, we can have all hearts. Diamonds and hearts are the red cards. We could have all spades, and we could have all clubs. So we have to have one of these suits accounted for. Okay, what's the probability of this? So let's call it all diamonds. All right, we already know what the denominator is. That's 2,598,960. Now you've got to think about this in a little bit different way than before, because when I'm choosing my 10, I'm not just choosing any old 10. I'm not saying just pick a 10. I'm picking a very specific 10, and there's only one of them there. Same with the jacks. I'm picking a very specific jack, and there's only one there. Same with the queens, kings, and aces. So for this probability, it's 1 over 2,598,960. Now that's not the only royal flush there is. Here you have a total of 4 possible royal flushes. So if I want the probability of a royal flush, I simply have to multiply my result by 4. The reason being is because if you go through and do all hearts, or do all spades, or do all clubs, you'll get this 1 out of 2,598,960, and for each of the 4 of them, and then when you add them together, you'll get the total probability. And you can see, I think I have the decimal equivalent for it. Well, let's go ahead and write it, because I want you to see what size we're talking about here. So I'm going to do 4 divided by 2,598,960, and that would be 50154. That's the probability that you get a royal flush. Let me put a note up here so that you can see why this works the way we do. For this one right here, I said those were the 10s. From the 10s, we would have had one specific 10 to choose from. We wanted a diamond, a 10 of diamonds. So there's only one of them, and I'm going to take it. And then for the next one, 1C1 would have also been true for jacks, queens, kings, and aces. It's all the same thing. So you can see it actually does fit in with our notation. For my last example, I wanted to do problem number 26 here. So what we have is a group of 7 people are going to be put into a line. And we are going to have 3 people that we're interested in, Doc, Frank, and Shem. Okay, and then assume order matters. Well, obviously, if we line up people, then order does matter. If 7 people are put into a line, that means the size of our sample space equals 7 factorial, since order matters. Now, what's the probability that Doc or Frank are the first two people in line? So you can completely ignore what we were doing as far as combinations. We're in permutation land now. So let me go ahead here and take a look. We want Doc or Frank as the first two people. So we could have Doc or Frank as the first person. And then whoever we didn't place in that spot will be the guy here. But then you have 5 people after him. So these 2 people will be independent of the 5 others that follow. And here, after those 2 guys are set, you got 5 people for the next spot. Then you've got 4 people for the spot after that, then 3, then 2, then 1. So you can see that this is equal to 2 times 5 factorial. And this happens to be 240. And so my probability then, let's just use the letter P. That'll be 240 over 7 factorial. Do I have that number? I think it's 5,040, but I'm not going to risk my memory on it. Let's go ahead and do 7. And it will remind you where it's at anyways. Math, PRB, choose number 4. Enter. 5,040 as I suggested. And you can leave it like that. I do want to show you one last thing though. The simplifying that you can do if you want to. It's not required, but it's so useful, it's not even funny. Our probability was equal to 2 times 5 factorial over 7 factorial. Once you get comfortable with the factorials, I can do this. In the denominator, I can do 7 times 6 and then stop at 5 because that goes to 5 factorial, and then I can slash them off. And you can see this is 2 out of 42. I can simplify even further. That's 1 out of 21. So they're almost enjoyable to simplify these things because of all the canceling that's done.